Hey, welcome back. Good to see you again. Thanks for joining the channel. This week on the bench I have a Pioneer amplifier. It's an SA-6700. Nice example. It's very clean. The only downside is some of the silk screening is wearing off in a few areas here. Not the the worst thing to happen, but a few letters are starting to flake away. This is a client unit. Came to me and he told me it's got a dead channel or it doesn't work or something to that effect. So let's see here. Don't even know if it accepts power. Let's see if it accepts power first. If not, we probably got an open fuse. So what does this have to say? Absolutely nothing. Open fuse. Okay. So let's take a top off and have a look inside. Very Spartan in design. It's got just the essentials. Power switch with a lamp, bass and treble controls. Nice chunky knobs and they feel nice. Good size to them. I like that. Headphone output. Speaker switch from off, A, B, and A plus B. It's kind of difficult to manipulate, but it's really stiff. Difficult. Okay. And we got loudness and a tape monitor. We have two power meters that read up to 100 watts, and then we have peak lamps above each meter to signal a peak. On this side we have a large volume control, our balance straight below it, and then a 3-position function switch. Tuner, phono, auxiliary. So yeah, it's just has all the essentials. That's all you need. Back has inputs for phono with a ground connection, tuner, auxiliary, and 1 tape loop, and then 2 sets of speakers. 3 courtesy outlets, 2 switched, 1 unswitched. So it's very basic. So the vinyl wrap has been removed on these sides. Probably started peeling away, and then they figured, well, it looks better, just peel it all off. All right, big reveal. Let's have a look. It's an interesting heatsink. It's cast. Don't see much going on. I do see the main power fuse here is blown. That's what it looks like to me. 3 amps at 125 volts. There's a secondary fuse here. It's 160 milliamps. That one looks intact. But that doesn't look like a 160 milliamp fuse, to tell me the truth. Looks like something else. It is. Wow. Okay. This one's popped open. It's hard to say if that was a hard short or if it was just an overload. Usually when you get a hard short, the fuse blows spectacularly and it creates this huge flash and bang inside that glass tube, and then everything is pretty much the inside of the tube is all coated with vaporized metals, but this doesn't look like it could have been just an overload, but we'll figure it out. So there's not much going on here, I tell you the truth. We have a little tone board up here for our bass and treble controls. Down this way we have mystery. We have another transformer down here. I don't know why we would have a secondary transformer in addition to the primary one. That is odd. We've got a power amplifier here. Looks like it's got those Batwing transistors, which might be difficult to find if we need. Power supply here in the center. Where's our big rectifiers? Oh, down here. Big rectifiers, okay. Power supply. We've got 8,000 microfarad at 50 volts. I think those are original. And then it looks like over here under this we have a phono stage Looks like they're using a couple of chips for amplification for the phono stage. Not my favorite, but Pioneer does what they want to do. Bottom plate comes off and gives you access to the printed circuit board. Lego block spacer here. Everything looks good under here. First thing I'm going to check is devices to make sure that none of them are shorted. We have to get to the bottom of why this amp blew a fuse. It could be something simple like replace the fuse and it will start working again. We don't know. But we are going to... Where are those devices? Oh, they're way under there. You can't even reach them. I was going to take my probes, but you can't even reach them with your probes. What a poor design. Let's flip this over. And we're blocked with those transistors sitting in sockets. That's weird. So maybe just remove 4 screws and the whole heatsink assembly comes up with the transistors. Let's do that. Alright, so I removed 4 screws, 2 on each side of this heatsink. Let's see if this is loose. Looks like it is. Oh, there's one in the center too, I didn't see. One more screw. Okay, so this should just lift right up, eh? Look at that. They must have known these transistors were going to fail. Okay, that's pretty cool. They have the 2 heat sinking stabilizers, heat sensing stabilizers here and here, and they attach under the main heat sink. So I got a new addition to the bench. It's a fluke meter, and this was a donation from one of my viewers. Thank you, Mark. I really appreciate it. He sent it to me. Mark used to be a service tech at a place in Kansas, and he's since retired, and he says he's got a lot of meters, none of them which he uses anymore. Maybe he does, I don't know. But he figured I could benefit from using one of these, so let's use it today. Let's go on diode check. No, I appreciate that. That's awesome. Thank you, Mark. Okay, this one's got good junctions. This one's open. Base to collector is open. Let's see if I can get this. Well, maybe I got, hang on, what have I got here? That's alright. No, those are okay. All these transistors are okay. No problems. No shorts. I don't see any shorts. No shorts. So, what's going on? Okay, so our next suspect would be the main rectifier diodes of the power supply. We might have a shorted diode there, which would cause high current on the primary. So let's go through and check those and see if those are all okay. It read a low value, but then it's charging up like it's a capacitor. So it's, let me try the other way. Starts off low. Starts off negative. try this one. It's definitely not shorted. Not shorted. Ah. That's shorted. We've got one shorted diode. Two shorted diodes. So maybe that's our problem. A couple of bridge rectifier diodes are shorted. Yep. Okay, simple enough. One. Let's get the other one out. Yeah, I'll replace all four of them while I'm at it, because maybe they're not adequate. Here's two. But for right now, we have two diodes. And these aren't very stout ones. They're GP20D. I don't know what those are. Let's see again. We have a short on this. Zero. Zero. My probes. Zero. Okay. Let me hunt up some new ones. Two bad diodes. So the four diode, I picked up four new diodes, and all the modern diodes that I want to put in have way thicker leads, so I'm going to have to drill out the holes for these old diodes. I'll remove those other two, drill out the holes for the four, and insert my new diodes. But first I want to take this outside and blow the dust out of it. It's kind of grungy inside, and there's a lot of dust and build-up, dirt. You can see it along here. And then we'll put those new diodes in, and we'll fire it up and test it out. Can't get this small bit into my drill, so I'm just going to use a pin vise. And just clean these holes out just so that they fit the new lead diameter. And it should just afford me just barely enough room to get those leads in there. They're quite thick compared to the original lead diameter. But then I think they're higher capacity diode too, so. Alright, new diodes are in. Let's button this up. Not often I see bad bridge rectifier diodes. These ones are kind of wimpy though, the ones previous. Alright, so that's in. So I think what we can do now is install the power transistors back and do a controlled power up and see how it's working. Okay, feeding it a tone. I got speakers connected up to my Variac. Turn it on. Let's ramp up the voltage and see if this thing comes to life. Okay, here we go. Something's smoking here. The resistor smoking. right down in here. Half an ohm. What is going on with that much current? Let's try that again. Yeah, we are drawing excessive current. So, let's figure out what that does. Something in this area here. I don't know what it does. Maybe it might be for the lighting. The lighting is all messed up here. There's wires cut. There's wires stuffed underneath the faceplate. So we might have a short in the lamps. But let me pull this faceplate off, and we'll see what's going on. There's something going on underneath here. I don't know. Okay, what is going on under here? Oh, we got bare wires and lots of electrical tape. And some LEDs here. Okay, we'll have to clean this up. This is okay, but this is not okay, the way it's done. We'll clean this all up. I'm scared there's a short here. Look at this. Wires were taped together. Let's try this one more time. Power up. Here we go. Yeah, we're still drawing excessive current. And we're still getting smoke. No power lamp. So something's going on. Okay. I determined the smoke's coming from this transistor. I can see there's some stuff oozing out the top, some silvery metal, looks like almost like molten metal came out the top. And this was quite hot when I first touched it. I burned my finger. And it is a BCR 3AM. I don't even think that's a transistor. That looks like probably a... Is that a three-legged device? Yeah, it's a three-legged device, but it's probably an SCR or a Triac. I don't know what they're doing with this. I'm going to have to look in the schematic and see what's going on. I thought it was one of these green resistors burning, but it wasn't. It was this thing. So let's pull up a diagram to see what's going on. Alright, so this explains everything. Protection circuit. This circuit protects the speaker when the DC voltage has been generated at the output of the power amplifier. When a DC voltage of plus or minus 8 volts has been generated at the output, the primary side fuse of the power transformer is blown and the supplied power is interrupted within 2 seconds. Shown figure 5. D26 is a Triac and is turned on when the gate input is plus or minus voltage. So what's going on here is using a crowbar. This is our power amplifier, our output, and if there's any DC on here, it goes through a low pass filter, and any DC that remains after going through this low pass filter, it turns either this transistor or this transistor on and triggers the Triac, which puts a hard short on plus VCC to ground. There's a resistor here too. I guess the resistor's to keep it from overcurrenting. And then it's supposed to pop the fuse, which kind of happened in our situation, but we also had blown diodes in here too. So maybe this is either we're getting a DC voltage on here, or this is turned on permanently and it's damaged. So we're gonna have to maybe pull this out of the circuit, pull this Triac out, and see if this thing powers up, and we'll see if we have any DC on our outputs. If we have no DC on the outputs, we can test the Triac, and if it's faulty, we'll replace it. Okay, so here's the Triac. And if you look at the top of it, you can see there's some silver spots. That's where, when it was hot, the metal juice came out. So I have the feeling this is damaged beyond use. So let's plug it in and try it out. This little tester should identify it and tell us if it's good or not. Otherwise it's going to indicate a hard short. Yeah, it's a hard short. See if I have another one of these. I probably do. Kicking around. Let's power it up without the Triac in place, and then we'll test for DC offset on the outputs, because we know our power amplifiers are working. We heard tones out of both channels, so that's okay. And the excessive current was this thing trying to crowbar the power supply to ground, and that's what we were seeing in the smoke as well. Okay, we're ready to go live. Got my watt meter, and this is across the right channel. That's the DC voltage. So let's turn this on. Went up to about 35 watts, came back down to about 12. No smoke, no fire. And we have 17 millivolts on the one channel, which is good. So let's try the other channel. 28 millivolts. Okay, so that amplifier is pretty healthy. We just need to find a new Triac. That was the problem. And we'll check the other associated circuit around it too, just to make sure nothing else is cooked. Okay, I do have a Triac. It is a BCR6AM, and the original burned out one was a, let's see here, it was a BCR3AM. So this is a 3 amp Triac, this is a 6 amp Triac, same thing, just more power, more current capable. I'm going to put that in. That will fix up our protect circuit. Now I'm looking at this thing and I'm thinking, I'm just shaking my head. I'm looking at all these old caps in here, and you know what I'm thinking. Yeah, you do. I'm going to go through and do one on this. I also have to service these switches. This is the main function switch here, and the tape monitor switch, but there is no access on the back side for those switches. I can't just desolder them. So what I'm going to do is pull this main board out. Not rip it right out, but I'm probably going to unfasten it from the chassis. I'll probably remove the back panel and swing that out of the way. I'm just going to leave all of the mains wiring connected, and I'll probably just remove the input board so I have some slack, and just move this back panel out of the way. That way I can unscrew the main board and just fold it out, just so I can work on the switches. That's my main concern, is getting these switches clean. They're problematic at this age, I'm guessing. I'm kind of debating whether I should just stick this Triac back in and then plug it in and run a test on it. I just don't know if I want to sacrifice the time, because I do want to see how these controls are reacting. I have a feeling they're all dirty and scratchy and cutting in and out. This is quite a old unit. This is mid 70s, late 70s, I'm guessing. These things I see that I just don't like is they're using these transistors legs as connector pins for these sockets. Now these pins on these transistors are just copper, nothing but plain copper, and they have a tin coating on them. But these ones also are coated with solder, which is a tin lead alloy, and that is not good for inside a socket. That is terrible connection for a socket. I know why they did this. They did this for servicing convenience, but also in the long run these will be problematic as well, because they'll start to oxidize and lose connection, and then you get scratchiness, you get channel dropout, you get maybe the amp will grenade itself, who knows. I like the idea of having this modular plug-in thing, but it's just, at what sacrifice do you give though? So I'm just going to leave it alone. I'm not going to do anything with that. But I do want to service this board. I want to replace all these caps except for probably the mains. They're probably still fine. I'm going to take them out and test them. And yeah, I also want to test a lot of these power resistors too. They're all wrapped in a kind of a fiberglass, I think that's fiberglass, sleeve. And you can't really see them. You can see if they're cooked or not. Typically you can see if they're cooked through the sleeve, but I don't know why they did this. I don't know why they covered all these resistors with that sleeve. I don't know what purpose that serves. It doesn't do anything for heat dissipation. It actually acts like an insulating blanket. Some of the things that these old manufacturers did back in the day, I just shake my head at, because they don't do them anymore because of X reasons. Yeah, and then another thing I'm going to do is I'm going to remove these LEDs from here, and I'm going to insert them inside the meter where they belong. Take place of the original lamp. The original lamp burned out, so I'm going to put those LEDs in their place so that has proper lighting from the inside of the meter, not from the outside. So that'll help with that. And clean pots and switches, yada. Not seeing any bad connections yet, any solder joints, but I know these black caps have to go. A lot of these black Nippon Chemcon caps are of the age they just need to go. So we're going to do that next. And you know what, I'm not going to bother testing this right now. We're going to test it at the end anyway, so we'll get a final tally on everything. And if anything crops up during that test, we'll fix it. All right, that's what we always do. So yeah, let me get started with removing the back panel and the main board. Okay, I know it doesn't look like much. Well, it looks like a mess. But just going through and doing pots and switches. I finished these 4, and I finished these 2. These need to get soldered back on the board. And just working my way through everything. Got to do the volume pot yet. I think I'll just treat it without removing it. Everything else looks good, except I have to clean this speaker switch. That's another thing I need to do, and it's kind of in a bad spot. I'm going to remove it, pull it out. These caps I test, they're fine. They test around 7,500 microfarad or so. They're going to go back in, and we'll use those again. And then after that, I can start assembly. Well, I still have some cleaning to do. It's pretty dirty inside. I'm going to clean a lot of the insides, make it look nice. And then I'll assemble it, and then we'll focus our attention on the lamps and the meters. Alright, looks like we got some problems in Pioneer land here. So I'm going through and checking transistors. I checked drivers on the drivers on the board here, and 3 of them are doing pretty good. One of them not so much. It's low on gain. It's considerably less than the others. We have like 130, 140 or so, and then we had one in the middle that was down around, can't remember, 60 or 80 or something. It was quite a bit lower than the rest. So I'm kind of mulling over changing these 4 out, these driver transistors, and then I went down and started checking the output transistors. Okay, I started checking these transistors, and these are supposed to have a minimum HFE of 40. These are power devices. Let's see, they're rated, they got some unusual ratings. 150 volt VC-EBO, 7 amps collector current, 80 watts dissipation, 8 megahertz transition frequency. So they're pretty robust, stout transistors, but they come in this goofy package that is difficult to match up and to replace. I can get transistors that'll drop right in and work, but they're a bigger package, and you can't use the mounting holes. You'd have to re-drill, and the lead spacing's different, the lead diameter's different, wouldn't fit in the socket on the board. So there's a lot of problems with using just any old transistor that's beefier or bigger. I want to replace this one here. Okay, sorry, let me get back to this. So we have 4 transistors here, minimum HFE of 40. So we got 68, 40, 23, and 78. So these 3 are good. This one here is problematic, and I have a feeling it's going to cause some issues with the sound in that one channel. So I want to replace all 4 of these. Problem is, what do you replace them with? Like I said, they got some kind of unusual specs. 150 volts for this transistor, but we don't need 150 volts because the amplifier only has a plus and minus 40 volt rail supply. So we don't need 160 volts or 150 volts. So my solution is to go with these transistors. These are 220 case style. And these are the D45H11 and D44H11. These are good stout transistors. They come in the right pin-out configuration and everything. Let's see, they have for stats, these are 80 volt transistors, and 10 amp collector current can dissipate 50 watts in this package, but we're going to change the package. And then it doesn't say anything about transition frequency, it just says it's fast switching speed. And that's going to be good enough, I guess. So how do we transplant this onto here? Do we just put it on and drill a new hole? I don't think so, because we won't get the dissipation. So we're going to need to figure out a way to get this transistor to dissipate the same amount of heat as these ones. And I think the only way to do that is I'm going to get a chunk of copper plate. This is 2mm copper plate, and I'm just going to solder it on like that and drill a couple holes, and there's our Batwing transistor. And we'll see how this goes. I'm going to get this started, and we'll get these made up. These ones have a HFE of about 150, if I'm correct. Let's try this right now. You can't read that, but I can. It says, oh, 102. Still better than 23. So I think I'm going to go that route. I'm going to replace these 4 with these, and then we'll test it and see how she runs. Still undecided on this driver transistor, if I just leave it alone or not, because it still falls within the range of what it should be, but it's just weaker than the other one in the other channel, and it's weaker than its complement. So this we'll see how this goes. Alright, I got the 4 copper plates cut to size. Actually, they're a little bigger they're wider than the original Batwing transistor, but I just cut them out of this plate copper. This was they had other transistors soldered on here, so I just removed them, and I have to grind this down. It's like a green. It's a little very thin layer of fiberglass on there, so I had to grind through that to make a surface to solder to. And then these are prepped. So these are cut to size and prepped. I want to drill the holes for the mounts. I think it's like 17.5 millimeters between the holes, center. So I'll drill these holes. I don't know if I drill them all, stack them all together and drill them at once. Might do that. And then I need to make sure that they're flat, because this one might be a little dished. Should be okay. I want them to make maximum contact on the back. And then I'll bring you back in, show you what it turns out like. Okay, so I got my transistors prepped. I chopped the tab off the top, and we're not going to use that tab. We're just going to solder them directly to the plate like that. So let's prep these. I think as a matter of course, we're just going to use some flux on all these just to help the process along. And we're just going to flood the back with solder. The thermal bond you're going to get by soldering these on is going to be far beyond anything that you can use as far as heatsink compound or anything like that. It's going to be right up there with liquid metal. So those are all prepped. I don't think I need to prep these. Let me see if I can even do this with the soldering iron. It probably doesn't have enough heat. I have to use a torch. Get some decent flux on there. Yeah, we're going to use a torch. Okay. So let's get some of these ready. A pair of tweezers because it's going to be hot. Get my propane and butane torch. Trick is getting this on centered. Center with the holes. Okay. Let's hold it down. Start applying heat. I'm running out of butane. Oh, nice. Can I do it before it runs out? I don't know. I need more heat than this. Yeah. Let me refill this. Okay, I reloaded my torch with butane. It's got a good flame going here. Press down on this and just start heating. There we go. Okay. There's our Batwing transistor. Clean that up and then we install it. So let me get these other three done and then I'll get back to you. Okay, I'm just going to give them a bath in alcohol. You can see them in there. Just going to give them a wash, get rid of all the flux. Any other crap. Just give them a go. I think they're coming pretty clean. I'm just going to give them Okay, I think we're good. Let's take them out and have a look. I think they're going to work great. And you know what, if this works out good, I'm going to make more of these because I have other amplifiers with Batwings in them. I think I got a Harman Kardon receiver that uses these in there. Got one channel dead. This might be the perfect solution. You don't have to do this. You can always drill holes in the heatsink and put a different case style transistor in, but then it complicates things as to, you know, spacing and lead size and all that jazz. this seemed like a better option, and I think this is going to work good. So let's get these installed. Actually, no. Let's test them. Before I do anything, let's make sure they're all survived the soldering. What we got? NPN gain of 143. NPN. I should mark that so I don't forget. This one should be NPN as well. NPN 148. You guys can't see that, can you? Let's try that again. Okay, 143. And that's an NPN, isn't it? $97. Let's see how this one turned out. $95. Okay, they're all good. Install these and be done. Not very flat. Not very flat at all. Almost, I don't know if you can see that, but there's a lot of dips and valleys. It's not a machined surface, that's for sure. They just sanded it. Now, work with what we got. So I'm going to mount these up, but the original mica washers, I can't reuse them because they're too narrow and too small. So I made my Batwing's too big. So probably what I'm going to do is I'm going to cut a sheet of sill pad, probably 2 sheets of sill pad to cover both transistors. One will cover this, one will cover this, and considering how uneven it is, I'll probably put some compound on there too, just to help along with the conduction of the heat. I don't think this thing gets that hot. It's only like a 50 watt amplifier or something, so I'm not concerned that way. But I am going to take this and wash it. It's filthy. And you can see the dirt on there. Give this a scrub, give these a scrub, and then we'll put everything together. And there it is. It's all done. Just got to tighten these down. Now I think these are called M100, no, MT100 case style transistors. They don't make them anymore, and if you want to go buy new old stock transistors, you're probably looking at $20 a piece from your eBay online sellers. There's some parts distributors that sell, you know, Japanese parts. They probably have some in stock. It's new old stock. They probably, and if you look them up, they're going to be $20 a piece at least. But like I said, you can also substitute in a lot of different transistors here, as long as you want to drill new holes and figure out the mounting. I like this solution because it looks factory original, and I think it's going to work great. Okay, those are all snugged down. We need to do a final test. Continuity. Where is my beeper thing? Okay, so we got continuity to the screws, which is good. But we need to know the copper plate is insulated. Okay. Everything's good. And the heatsink fins, there's no connection. Everything's good. We got a little bit of, okay, should just drop right in. There we go, I think it's in. Yep. Alright, I'll secure this down and then we can get on to the meters. Okay, onto the meters. So this is what I pulled out of the front faceplate. They had these LEDs, they were stuck underneath the meters in this spot and this spot, and I took them both out. It's not really the right spot for them. They were kind of blocked from getting light up into the meter. So what I'm going to do is I'm going to open this up, and if it will let me. Let's see here. I'm just going to pull off the sellotape. Somebody's been into these things before, I think, because the sellotape is really okay. All right. So we should be able to open this up. And my plan is just to remove this bulb. This bulb is done, pretty sure of it. Let's see. Let's see here. Yeah, it's open. So let's get rid of this bulb that's here. First off, let's get rid of this. Okay. And we'll solder our LED onto those two tabs. Now, I was looking at this LED and I was wondering what kind of a contraption is this? It has two LEDs. Looks like they're wired in series on this board. You can't see it, it's all white and painted over. But on the back it has a dropping resistor and looks like two transistors. But I don't think they're transistors, I think they are, see, they didn't even have these soldered, they were just twisted. Get rid of that. So I don't think they're transistors, I think they're rectifiers, and they have like a bridge configuration. Because I tried this on power, and I put 8 volts to it, and it lights up at around 9. Let's try it again. Let's do it for reals this time. Okay, let's get... What do we got? I got 8 volts in the power supply right now. So 8 volts. Here's 8 volts, okay? And we're drawing 9 milliamps. Now if I reverse this and connect it up, we got 9 milliamps. Now if I turn this up to 12 volts, it gets quite bright. There's 12. And we're drawing about 23 milliamps, or a quarter of a watt. That is too much power, I think. So we're going to have to back this down. Somewhere between 8 and 10 volts would be good. There's 8.9. Oh, that's 9 volts. It's pretty bright. 12 milliamps. Somewhere around that area. I don't want to go too crazy because what we're trying to do is light up this meter, right? And, yeah. Now I think this meter has this aluminum plate in here to kind of block the light from going down and out the front. I think what I'm going to do is I'm going to have the LEDs pointed towards the aluminum plate, and then the aluminum plate can reflect and diffuse the point source of the LEDs, and we're not going to get such a harsh light. It's going to be more flooded. So let me solder this in. Get rid of this. We'll solder this in circuit. Let's do that right now. Let's see if we can clean this up. Okay. It did splash a little bit there. So I should be able to just feed this into the hole. Pull this one through. Trying to wiggle the wires through the holes and it's not cooperating. If I bend these up, there we go. Alright, pull this one tight. Not quite centered, but it's good, I think. Let's pull it this way. Okay, I'm going to leave it like that. Okay. All right. That's not going to interfere with the mechanism at all. And it brings connections out to here. And we could feed it with an AC signal, a DC signal of either polarity. I'm probably going to feed it with a DC signal so that way we don't get any strobing. And it's pointed down towards the bottom corner here. So if we put this back on, and I tape it shut, let's connect our power supply and see how this lights up. Ooh. But then you won't see that part, you're going to see that. So I'm going to have to turn it down a bit. It's going to be too bright. Okay. Okay, for the meter lamps, I wired them directly to this post here. Beside the electrolytic caps, there's a post. And then there's a post here right in front of this regulator. Now I measured 10 volts DC between these two posts. And this is for feeding the tone board. I think there's a wire that goes to the tone board. But I just tapped directly off here and fed it directly to the back of the meters, going into LED lamps, and it works not too bad. It's a little bit on the bright side, but I think it's going to be okay. I could show you here. Just let me get the camera repositioned. So here we are turning it on, and they're both even. Okay, the service manual is very confusing. It doesn't give you any procedure for an adjustment. It gives you a procedure for a check. So what they want you to do is connect up a 8 ohm load, turn the speaker switch on, connect the voltmeter between these test points. Now they're really difficult to see. I don't know if you can see it down here beside the emitter resistor. There's a pin sticking up. That's one test point there. And then hidden by this fin, there's another test point on the other side of this emitter resistor here. So that's where you connect your voltmeter to those two pins. And for the other channel, you can see one pin right here beside this emitter resistor. There's a pin. And then there's another pin buried underneath all these wires and on the side here. So we got the 4 test points. So connect the voltmeter to 2 of those test points, and you turn it on and you read the voltmeter. Now this is where it's kind of confusing. It's telling you if it's within the range of 10 to 70 millivolts, you just leave it alone, you don't do anything. If it's below 10 millivolts, what they want you to do is cut this little jumper wire here, this yellow jumper wire. See that? You cut that and it adds a little bit of extra bias. And there's one on the other side here too. You can see it poking right there. There's a little wire, yellow. Okay, I got my meter connected. Let's try it out. Turn this on. I need to turn on the load. And let's do this. And we got to plug it in too. There we go. So we're not getting our 10 millivolts for sure. We'll let it settle for a bit and then we'll see. It's climbing up, but it's not climbing up fast enough or far enough. Okay, I think what I'm going to do is cut this wire. They should have just put it on the back side of the board, but I'm just going to reach in here, a pair of nippers, and snip that wire. Hopefully I'm not going to short everything out. So here we go. There we go. 10 millivolts. That's exactly what we wanted. Okay, here we are, the other channel. Let's turn it on. Let's see what we get. Same kind of thing. Yeah, I think I'm going to cut this one too. Probably what I'm going to do is I'll just remove those cut ends of that jumper. Remove them completely. That way there's not a free end floating around on the board. I'm just going to cut this other one right now and see how it changes. It should come right up. That only went up to 7. Okay, for the power meter test, what they want us to do is connect a load to the speaker, turn speakers on, feed it a signal, and adjust the output level for 6.32 volts RMS. And then we're going to adjust the meter to match and the minus 10 dB mark, which is right in the center, right above the word watts there. So let's turn this up. Turn off the speakers and turn on the load. Let's turn this up to 6.33. 6.32. 6.35 right there. Let me turn it down. Just turn it down a hair. Close enough, 6.33. And our meters are very close. Very, very close. So I'm going to see if I can just tweak them up a little bit. Okay, let's see this one here. Put it right on 10 in the left channel. Perfect, right there. Okay, we're done. Now I encountered another problem here that I have to fix. These peak lamps, I don't know if you can see them. Watch when I turn up the power. They come on, but they're so bloody dim you can't even see them. So I'm going to replace these lamps, I think. Alright, we're all wired in for a power test. Let's do this. Now, I've had this thing powered up before. Let's see here, we got speakers. Okay, that is working great. Let's turn it to speaker system A where the load is. Let's turn this thing up. We've got 1000 hertz tone. Let's go up to clipping. Right there is clipping. Back it off. Probably close to that point. Okay, so we'll see how this does in 10 minutes. And what we have right now is 20.05 volts RMS on the output. Got a cold start. Let's see how it goes. Right now we're drawing 183 watts on the input. So for full load voltage on the power supply, both rails, we got 64.3 volts. If I take the load off, climbs up to 77.7. Okay, so we're up to 10-minute mark here. Things are heating up. This heatsink though is doing pretty good. I don't think it's more than 40 degrees. 41. And it doesn't seem to be getting too hot. 44 at the bottom. I don't know if you notice this, what's going on here. We're seeing a little bit of a, it's like it's breathing. You see that the right channel is clipping top and bottom now. I think once it warmed up it started clipping. And you can see it's doing a little bit of this. I don't know if that's some kind of a low frequency oscillation or what. Our power supply is holding up. And our power output held up. We're still at 20.1 volts RMS. So I think this is a success. I still want to investigate why the right channel clips a little earlier than the left. So let me measure the output of that channel. Maybe it's a little higher and it's just... Ooh, the heatsink is hot. Okay, let me try this side. .45. It's a little bit higher. Let me see if I adjust this down. 20.0, and our clipping pretty much gone away. So that right channel's maybe a little bit higher gain than the left. I think they're both doing pretty good. For what, we're at 12 minutes now, full power. We're not even hot. It hasn't blown up. It's doing well. So I think our Batwing transistors are a success. That's what I'm going to say. And we're going to end this test here. And we can go and do some square waves now. Alright, here's a 1000 hertz tone, square wave at reduced power. Looks like bass cut, bass boost, treble cut, treble boost. Looks like we have a ring on one side. So you can see the ringing on the one channel. It wants to ring. Loudness, balance, oops, balance, it's all working good. Okay, let's go up in frequency. I'm wondering why we have a little bit coloration on that left channel. Let's go up in frequency. Five kilohertz. Still apparent, isn't it? 7, 8, 9, 10 kilohertz. That is 21 kilohertz. That's not bad, but we still have a difference in one channel to the other. And I don't think it's in the tone controls. This is treble cut, treble boost. Treble boost. See the difference in channel here. So I'm going to have to do some more investigating as to why this looks different one channel to the other. That's not healthy for an amplifier when you have channels doing different things. Okay, so it was a good test. We know it's going to handle maximum power for a long time. We still have another thing to hunt down. Let me go through this some more. We still want to deal with these two peak lamps because they're not lighting up very well at all. Alright, so I'm trying to figure out this signal path for this amplifier. Signal comes in on the auxiliary tuner inputs, bypasses the phono amp, goes into your switch, your selector switch, your function switch, and from there it goes through your balance pot. Okay, and from there it goes right into the volume control. From the volume control it goes into the input of the power amplifier. So there is no preamplifier on this thing. There's only volume attenuation at the beginning. Power amplifier tone controls are incorporated in the power amplifier feedback, I believe. This tone control, the tone stacks up here, and the wiring kind of goes between the outputs and the inputs. But I have a feeling I got a tolerance issue with some of these parts here, either capacitor or a resistor. Maybe that's why we're getting such a huge difference in our square wave. You can see it up there. The left channel on the top doesn't look like the right channel. That's still at 21 kilohertz. Let me turn this down. Turn it down to about 5 kilohertz. You can see the difference in the signals. So we might have an open capacitor or something on the top channel there, the left channel. That's what I'm hoping. I'm going to go through and check a bunch of components and see if we can figure out the cause of this. Okay, have a look at this. I see the top channel twitching there, the left. See how it's, I think it's starting to fail. What I did is I sprayed the long tail pair, the differential pair. It's one of those 5-pin package devices. It's a 2SA-798. I think that's the one. If I spray it again, see how it gets all twitchy. Let me see here, spray some other transistors. Getting very twitchy. Might have to replace that transistor. Heat it up with my finger. Something definitely going on in that channel. Let me spray the one in the right channel, just for comparison. Let me see here. See, the right one's stable and it didn't move. Left one is twitching. Let's put some more power to this thing. Okay, up we go. It's clipping now. It's 5 kilohertz. No, that's 11 kilohertz. Sorry. Let's turn it down. I'm trying to blow up this amp. Now we're definitely going to have to deal with that differential input pair. So this is the long tail pair. This is a 2SA-798. You can see it there. Little 5-pin device. And this is what I suspect is all twitchy. Now I did check the gain on both transistors, and they're both about the 360 range. Pretty close to each other, not bad. But my plan is to replace them with two SA-992s. And let's just check what our gain is on these ones. I don't know if you can see this. So we're about 360. So I'm going to tie the emitters together because that's how this is configured. And tie the emitters together, and we're going to thermally couple the two transistors, and then we'll put it in and see how it goes. Okay, so I switched out that differential pair, the long tail pair that in the input of the right channel. Let's switch it on and see how it does. On the square wave test, and we still have the same imbalance. You can see we still have the same imbalance, but I didn't expect that to change at all because all we were doing was replacing those transistors, and they were a little twitchy before. And it seems if I spray that area again, we'll see if that twitchiness is gone. Here, let me spray this. Soak down the area, and I don't see any twitchiness happening. Stable. So that part's been fixed. But we still have, oh, that's the driver transistor I just sprayed. And it's doing twitchiness on the spike. Let's replace those drivers. I have to find a good substitute. Look at it, it's twitching again. Maybe it is a bad driver. Or a dodgy resistor here. Okay, so I'm just going in with a cold spray and trying to zero in on what part is actually defective. Here's the long tail pair that I replaced. Get out of the way. And everything's good there. But then when I sprayed this transistor here, it starts doing the twitch. So I have a feeling that might be the one. And I replaced this cap, no change. Sprayed this transistor, no change. Sprayed the driver transistor, no change. Sprayed this driver transistor, no change. So that one there seems to be the culprit. So let's pull that one out. Which one is that? That is a 2SA-912, I believe. And that is probably the voltage amplification stage. That one might be weak and twitchy. 2SA-912. So my mistake, that transistor was not a PNP, it was a 2SC1312, which is on my list of known defective transistors and should be replaced. So I'm going to replace it with a 2SC1845, and let's see how this thing is going to work now with a new transistor in it. So let's turn it on. And let's have a look at the waveform. So there's our square wave at, what are we doing? We're doing 3 kilohertz. I'm going to spray some cold on that area that I was spraying before and make it twitch. Gonna flood things here. That twitching's gone. I thought it was gone last time, but it wasn't. But it looks like it is stable now. We still have a little bit of a twitch on this, on the peak here. It seems it's twitching up and down. Let's focus in on that. Let's get rid of this channel. We know that channel's good. Let's do something like this. You see, we still have a twitch. Yes, it's still twitching. I still have one more transistor here to replace. There's some ceramic caps here too, which I'm questioning. See, I just sprayed them and it kind of went weird. Yeah, let's replace some of these caps. Let me show you. You see it's all wet. See right here, there's this cap and this cap. This is the ones I was spraying. It was getting all twitchy. This is the transistor I just replaced. This is an original. This is our long tail pair. And there's ceramic disc caps in here. There's one here, here, here. I'm gonna see. I have a feeling one of them might be bad. I've seen caps like that go bad before, and they're really hard to diagnose because you usually assume it's a transistor or resistor or something. The ceramic caps you really don't suspect very often because they don't go bad, but sometimes they do. So this one wants to play hardball here. I've been doing a lot of work and I'm still not being able to pin down what's going on. I actually swapped some transistors from one channel to the other to see if the problem went with the transistor, and nope, didn't happen. So I kept spraying around here, and I went up here. There's an area just above the long tail pair. There's a resistor. It's an odd value, very odd value, and I measured it. It's kind of out of tolerance by about 3 or 4%. It's a 110K resistor, and I'll put you on the scope and watch what happens when I spray it. Okay, here we go. I'm going to try and get this resistor without flooding everything else. Oh, no, it's not going to misbehave. Give it another shot. I'm in the right area though. Spray some of these other resistors. See, this is the problem. It doesn't want to misbehave now. And yes, I did have it just going before I turned the camera on. So let's keep trying here. Let's try the long tail pair. Get it nice and cold. Got 2 new transistors there. It shouldn't do anything. The resistor is a diode here. Diode seems stable. Okay, I'm spraying this 2 SA-912. It's getting twitchy now. I might have to swap these two from channel to channel to see if that problem goes with that transistor or not. I don't know what to tell you. I'm beginning to think I might just put this thing in service and start listening to it, and if it starts developing a weird crackling or hiss in the one channel. I replaced some of these caps, and some of these ceramic disc caps I replaced because they're known to go bad eventually, but it didn't seem to make any difference. So I'm just going to run with it for now. It looks like it is kind of settling in. As far as the waveform starting to, if you look at the waveform here, we're at 3 kilohertz, and the waveform's starting to behave. Like we're losing that spike on that left channel. If I turn the treble up, it's quite pronounced. There it is there, but it's in both channels. There's center. So it's starting to look a lot better. I think it's just as it, if I leave it powered on long enough, it seems to just kind of fix itself. Okay, I'm going to stitch this in the middle somewhere. This is a week after I finished the unit. Now I ran with the amplifier for about, like I said, a week, and I wasn't pleased with how bright the lamps were. So I wanted to turn them down. So what I did, I made some modifications here. So this string here, from here, this point, goes through these 3 resistors, through this transistor, through this resistor. This goes off to the lamps, okay? The lamps are supposed to be fed with 7.5 volts. But I was getting like 10.5 volts on this line going to the lamps. That's why they were so bright. Reason being is there's really no current. The LEDs now, and there's no current. If I had incandescent bulbs, there'd be a lot more current. There'd be voltage drops across these resistors, and it would balance itself out. But here I don't have the right current. So I have my 40 volt supply here, and these 3 dropping resistors are supposed to drop it down to minus 20 volts. But it wasn't. It was coming down only by 4.3 volts. So this was about 36 volts here. So what I did is I replaced, there's 3 62 ohm 2 watt resistors in series, totaling 188 ohms. That's what I measured. So to accommodate the LEDs and the lower current, I removed these 3 resistors and replaced them with 2 470 ohm resistors, 2 watt. And that's for a total of 940 ohms. That's what I calculated. And what that did is it dropped this negative 40 volts down to negative 20 with the current I'm using. And that brought this back in line and this voltage back in line. Not that it really matters, because the transistor would compensate for it. It should regulate and compensate. But even after I replaced these 3 resistors with the 2, I was still getting like 10 volts. And the problem being is this resistor here, I can't even read it. It's 124, I think, or 114. So I can't read that. This resistor, 15 ohms, was it's like a current sense, because the voltage drop across here, if it reaches Zener voltage, then it starts. So this voltage drop across this resistor was only about 900 millivolts or so, far too low. So what I did is I increased this resistor to a 150 ohms, and that provides enough voltage drop across this resistor to activate the regulating part of this circuit. And now I get about 7.8 volts going out to the LEDs, and it's a lot softer light. It's not as bright. I can show you where I made the changes here. Just hang on. Okay, here's that series pass transistor. It's a 2SB507. There's the 2.7 volt Zener right in here beside it. And I don't know if you can see it. These 2 resistors here are the 470 ohms at 2 watt that I used to replace the 3 resistors that were in here. And the resistor I changed was this one right here, and that's now 150 ohm, and this provides proper regulation now for those LEDs. Not that they need regulation, they don't need it, but it just helps. If you have fluctuations in line voltage, your lights aren't going to flicker brighter and dimmer. So I'm going to leave it at that. That's the modification I made to the lighting circuit. And we can see it, I'll turn it on. Even with the lights out, it still seems a little bright, but it's a lot better than what it was. It's more softer, I'd say. It's not as harsh and not as bright. So that's what I'm going to stick with. I'm also getting light flooding out the bottom, so I'm going to remove the faceplate and I'm going to add some foam strips right about here just to block the light from coming down, because it was bleeding out through these switches and it was illuminating the surface it was sitting on. So I'm going to block that light. So there it is. I'm going to end this one here. A lot of parts went into this, a lot of work. It came in dead on arrival, and we fixed up a lot of stuff. First we had a blown fuse, main power fuse, and that was due to this shorted Triac, this BCR3AM. This Triac is in a protection circuit, and it's supposed to short out the power supply if there's a DC offset on the output, but this Triac was faulty. We also found 2 bad rectifier diodes in the bridge rectifier, the main power bridge rectifier. So that's been all fixed. Our Batwing transistors, we had one here that tested really poor, so I opted to replace all 4 of these as a set, and that actually went really well. I'm pleased with that substitution I made. Now that's, you got to remember, that's not for every Batwing you come across. You can't really do that. You have to size up the transistor specs for the sub you're using for the circuit. Now these are 160 volt transistors, but this only uses plus and minus 38 volts for the rails, so we're well within the range of the new transistors I put in. A couple burned out lamps, we removed them and we replaced them with LED modules, and they're lighting up really nice. All the caps needed to go. Nippon Chemcon black caps are dead at this time. They're 50 years old. They're garbage. Values are all over the place. Their ESR is all over the place. So it's nice to have a fresh set of caps in, and everything's nice and balanced. So you can see the peak meters are now working. See how bright they are. I had to remove these old dead LEDs. These are actually still working, but they're so bloody dim you can't even see them anymore. You have to look at them in the dark room, and then they light up. But I took these out and replaced them with modern super brights, and you can see here it comes as you bring it up. It looks pretty good for peak reading, peak lamps. So that's it for this one. I'm gonna test drive this one for quite a while, because I'm concerned about that amplifier, that twitchiness in that amplifier. I just want to make sure it doesn't come back. And we'll move on to the next one. Lots of stuff coming up, so take care, and we'll see you in the next one. Thanks for watching.